Mixing problems. A typical mixing problem involves a tank of fixed capacity filled with a thoroughly mixed solution of some substance, such as salt. A solution of a given concentration enters the tank at a fixed rate, and the mixture, thoroughly stirred, leaves at a fixed rate, which may differ from the entering rate. If big Y, if Y of t denotes the amount of substance in the tank at time t, then Y prime of t is the rate at which the substance is being added minus the rate at which it is being removed. The mathematical description of this situation often leads to a first-order separable differential equation. We can use the same type of reasoning to model a variety of phenomena: chemical reactions, discharge of pollutants into a lake, injection of a drug into the bloodstream. Example 6. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt remains in the tank after half an hour? Solution: y of t, let y of t be the amount of salt in kilograms after t minutes. We are given that y of 0 equals 20, and we want to find y of 30. We do this by finding a differential equation satisfied by y of t. Note that dy over dt is the rate of change of the amount of salt. So, equation 5, dy over dt equals rate in minus rate out, where rate in is the rate at which salt enters the tank, and rate out is the rate at which salt leaves the tank. We have rate in equals open 0.03 kilograms per liter, close, open 25 liters per minute, close, equals 0.75 kilograms per minute. The tank always contains 5,000 liters of liquid, so the concentration at time t is y of t over 5,000 measured in kilograms per liter. Since the brine flows out at a rate of 25 liters per minute, we have rate out equals open y of t over 5,000 times kilograms per liter, close, open, 25 liters per minute, close, equals y of t over 200 times kilograms per minute. Thus, from equation 5, we get dy over dt equals 0.75 minus y of t over 200 equals 150 minus y of t over 200. Solving this separable differential equation, we obtain the integral of dy over 150 minus y equals the integral of dt over 200. The negative natural log of 150 minus y equals t over 200 plus c. Since y of 0 equals 20, we have the negative natural log of 130 equals c. So the negative natural log of the absolute value of 150 minus y equals t over 200 minus the natural log of 130. Therefore, the absolute value of 150 minus y equals 130 e to the power negative t over 200. Since y of t is continuous and y of 0 equals 20 and the right side is never 0, we deduce that 150 minus y of t is always positive. Thus, the absolute value of 150 minus y equals 150 minus y, and so y of t equals 150 minus 130 e to the power negative t over 200. The amount of salt after 30 minutes is y of 30 equals 150 minus 130 e to the power negative 30 over 200 equals approximately 38.1 kilograms. Sidebar, figure 10 shows the graph of the function y of t of example 6. Notice that as time goes by, the amount of salt approaches 150 kilograms. See figure 10.